This lecture is on the anatomy of the zonule. And actually the zonule represents a series of delicate radially arranged fibers that collectively are called either the suspensory ligament of the crystalline lens or just for short the zonule. It holds the crystalline lens in position and its fibers arise from the epithelium of the ciliary processes running forward toward the equator of the lens, and on doing so they fuse to form about 140 bundles. On this diagram here we can find the zonule connecting the ciliary processes of the ciliary body to the equator of the crystalline lens, and here they are in color. On magnifying this area of the globe, we can find that these are the ciliary processes, and this is the zonule connecting the equator of the crystalline lens to the ciliary processes. These are the connections on a posterior view showing the crystalline lens centrally within the diaphragm formed by the ciliary processes. And in patients suffering from subluxation of the crystalline lens, we can clinically see the zonule as these crystalline fibers connecting the ciliary processes behind the pupil and the iris towards the crystalline lens. As you can see, these are the fibers we are talking about. Within the zonule, there are three types of bundles. First are the large bundles that are straight, reaching the lens capsule in front of the equator, and they together form an anterior zonular sheet. The middle bundles that pass from the tips of the ciliary processes directly inward to be inserted immediately at the equator of the lens, and the smaller fibers that curve backward to attach to the posterior surface of the lens, forming what is called the posterior zonular sheet. So they can be classified into the anterior zonular sheet composed of large bundles, the middle bundles that are directly attached to the equator, and posteriorly the posterior zonular sheet, which are smaller and attached to the posterior surface of the lens. As you can see, this is a section, a three-dimensional diagram of a section of the crystalline lens at its periphery, and we can see the anterior surface and the posterior surface. Here, number A represents the anterior zonular sheet of large fibers that attach into the anterior capsule of the crystalline lens. And B are the middle ones, which are attached to the equator of the lens. Third are the smaller fibers, the C portion, that attach to the posterior surface of the crystalline lens. The A anterior fibers form a sheet called the anterior zonular sheet, and here represented by the green D, and the posterior zonular sheet, which attaches to the posterior surface of the crystalline lens, represented here by the pink letter E. Now at the lens, the fibers break up into fine fibers and become embedded in the outer part of the lens capsule. During near vision, elastic lens capsule is under tension, causing the lens to assume a globular shape, while during far vision, the zonules pull on the crystalline lens by pulling of the ciliary muscles, flattening the elastic lens capsule, permitting the eye to focus on distant objects. This process is called accommodation for near, and simply the ciliary muscle contracts where the circular fibers act as a sphincter, moving the ciliary body inward, and the meridional fibers pull the choroid and ciliary body forward. This relieves tension on radiating fibers of the zonule. and this allows the elastic lens to assume a more globular shape, as we said. At the same time, the sphincter pupillae muscle contracts and the pupil becomes smaller. With advancing age, the lens becomes less elastic, with the ability to accommodate being lessened, and this is the known optic condition of presbyopia. Now, understanding the anatomy of the crystalline lens, the zonule, and the ciliary body, we may briefly go through the theories of explaining the phenomenon of accommodation for knee. The first is the Helmholtz theory that states that ciliary muscle diameter change is responsible for change in shape of the lens. Simply, the crystalline lens is described as a bag of an elastic tissue with contents of plastic material. Elastic means it's under tension by the zonule and the ciliary muscle that is at rest. Once the ciliary muscle contracts, the ciliary ring becomes smaller and the zonule relaxes and curls, and the tension in the lens capsule is relieved and it becomes therefore rounder, increasing its thickness and its optical power. The second theory is the Shaker theory, which states that increase in the zonular traction at the lens equator is rather the factor that leads to increase in lens diameter. In this theory, the meridional fibers contract, pulling on the center of the zonular fibers that become tight, and in this way the anterior central part of the lens becomes thicker and more steeply curved, increasing the thickness of the crystalline lens. This footage here probably shows a combination of both that occurs actually. Once the ciliary muscle contracts, as you can see, the ring becomes of less diameter, relieves the fibers that are anterior to the equator of the lens, letting the crystalline lens become of a more globular shape. At the same time, the posterior fibers, due to contraction of the meridional fibers in the ciliary body, become tenser, and this tension here leads to increase in diameter of the posterior surface of the crystalline lens. So it's a reciprocal process between the anterior and posterior zonular fibers. The anterior zonular fibers become lax and the posterior ones become tense, and this leads to the complex process of increasing both the anterior and the posterior surface curvature of the crystalline lens. Thank you very much.